Hi students, today we are going to see the chapter 11, that is work, power and energy of class 9 CBSE, chiefly given as work and energy. So we also see the other parameter called power, which is derived from work, and of course the other areas. Now, so after completion of the session, you must be in a position to know what is work, like how it is defined from the two variables or the two parameters, force and displacement. Then what is a unit of work. Then once you understand work clearly, then you'll also come to know whether the work done is positive or negative. Then we have some small numericals we'll see with respect to work. Then it is energy, because what is energy parallelly with work. So energy we see as the ability to do work. Then different forms of energy, because work and energy, they'll have the same units. So we see, because both in the same parallels. And then we see kinetic energy and potential energy, which are the two basic forms of energy. I mean to say, as far as our work energy portion is concerned, we study different forms of energy, out of which the main energy forms we study are kinetic energy and potential energy. Next, we see the relation for kinetic energy in terms of velocity. Then we have potential energy. Again, we see the definition of potential energy, and of course on what factors it depends, right? Potential energy is a function of gravitational acceleration and height, of course cm. The units for P and K. Now, because energy conservation theorem always applies, so we study transformation of energy, and so how one energy form is converted into other energy form. Then we have finally a rate of doing work as power. So we talk about power as a rate of doing work, and again the units of it, okay, are considered and detailed. Finally, some of the commercial units of power, whether when it comes to electrical energy or electrical power, so how it is rated and how it will be calculated with regard to electricity, and these things are understood. So let us have a small this one on energy, right? Okay, basics on energy, prior to which we study work. So the first and foremost thing is work. So what is work? Work is defined only, I repeat, work is defined only when an amount of force acts on a particular object and gets some displacement in that object. So when it acts in a particular direction and gets some displacement in the object, which is at standstill or rest, then work is said to be done on the object. So we can say work is said to be done when a force acts on an object and the object is displaced in the direction of the force. So there must be a displacement in the direction of the force. And work done is mathematically given as product of force and displacement. Now, if you look at that is mathematically W is equal to F into S. The unit of work would be, it is joule typically, because energy as well as work, they have same units, so which we call it as joule. See, what is joule? Because just now we have defined when force is applied on an object and gets a displacement in the same direction as that of force, then work is said to be done. That means, because the unit of work is joule, 1 joule is nothing but when 1 Newton of force acts on a body, on an object, and gets a displacement of 1 meter. So that's how we can define joule, right? Now, so accordingly, we can give a small example that when 5 Newton of force acts on a body and gets displacement of 2 Newton in the direction of the force, then the total amount of work done is said to be 10 joule. Next, the representation also, you can see it is with capital symbol J. Now, the second thing is work done, whether it is positive or negative. Anyway, we have seen just now work as vector. So if you look at the magnitude part of the vector, then work done by a force may be positive or negative. So when work is said to be done by the object or on the object. So work done by a force is positive if the force and displacement are in the same direction. In contrary, if the work is done by a force is negative if the force and displacement are in opposite directions. So other than that, No, we don't have any other options like in quantity. So work done by a force is again, there is only one option, that is it can be 0 if the displacement is also 0. If there is no displacement, then that too we can say it is displacement, work done is said to be 0. Now again, so therefore work done by force is 0 if the force is perpendicular to displacement. That is one more option, like because work is a vector, when you multiply, and displacement is also a vector. When you multiply one vector with another vector, then it becomes again a product of two vectors. It can be a cross product, or we call it as a vector product. It can be a dot product, or it is a scalar product. So in the vector product, so we are not considering the vector product here. When you simply consider the scalar product, that is f dot s, then we have cos theta coming into picture, fs cos theta, because magnitude wise it is w not only force into displacement, it is also force into displacement into cosine of the angle between cosine of the angle between force and displacement. That would be theta, right? Cosine of the angle between force and displacement, that is theta. Now, so once you understand, so therefore here the displacement, just now we talked about the work done on an object, and when it gets the displacement in the perpendicular direction. So the displacement would be, the angle between the two vectors will be 90 degrees, and accordingly the work done will be 0, because cos 90 becomes 0. Now, similarly, some of the examples that practically we come across are in the day-to-day life. When we lift an object, the object moves upward in the direction of force, right? So, yes, so therefore here the work done is positive, but there is the force of gravity acting downward in the object. So work done by the force of gravity is negative. Like, we'll take one more example. Make a porter lifts a luggage of 15 kg from the ground and puts it on its head 1.5 meter above the ground. So calculate the work done. So we can say it is simply mass of the luggage is 15 kg and displacement is 1.5 meters. So it is 10 meter per second square. Acceleration due to gravity, if you consider as 10 meter per second square, then actually work done is equal to force into displacement, that is m into g into s, 15 into 10 into 1.5, 150 into 1.5, 225 kg meter per second square. So it is joule is nothing but kg meter per second square. Just now I told Newton into meter is as same as yes, because Newton is equal to m into a, and it is kg into meter per second. It is for me. That is force is equal to m into a. So therefore kg meter per second square. That we can consider, right? So F into S. But here actually, if you take force as kg, that is that you can see weight and force. Here force is nothing but the weight. So again, kg into second, that is you can say F is equal to m into g into second. So that is how it comes as kg meter per second square into displacement meter. So it is nothing but kg meter per meter. Actually it should be defined as kg meter square per second square rather. Anyway, 225 Newton per meter as 225 joules. Now energy, see, if I have to define energy of an object is the capacity of doing work. So here it is not only of one object, of a system we can consider as a whole. So when you consider system as a whole, energy of a system is the capacity to do work or ability to do work. So the unit of energy is as same as that of the work done, which is joule. So work done, that is there is again actually, whereas joule is a SI unit of energy, we have one more unit of energy called CGS unit of energy, that is ergs. So therefore one joule is equal to we have a relation that 10 power 7 ergs, and just like how where Newton is equal to 10 power 5 dynes. So therefore 1 joule is considered to be 1 kilojoule, and therefore kinetic energy, it is now. So once you define energy has the ability to do work, and there are two different types of energy. One is by virtue of its movement, and one is by virtue of its position, right? So whereas now first let us look at kinetic energy, which is by virtue of movement. So energy possessed by the object due to its motion is said to be kinetic energy. And like all moving objects, they possess kinetic energy. A falling coconut, a speeding car, a flying aircraft, flowing water, blowing wind, running athlete. So they all possess kinetic energy. Kinetic energy of an object basically depends on mass as well as velocity, right? And I mean to say speed. So an object moving faster has more kinetic energy than the object moving slower. Now, kinetic energy possessed by an object of mass m and moving at a uniform velocity. Here one must underline that statement that uniform velocity is not non-uniform velocity. So therefore it is moving with some uniform velocity v is given as kinetic energy is equal to half into mv square, half into mv square, right? So half into mass into velocity square, half into mass into velocity square. Now you can take an example here that object of mass 15 kg, object of mass 15 kg, right? Moving with a uniform velocity of 4 meters per second. What is the kinetic energy possessed by an object, right? It is mass of an object is 15 kg, and of course velocity of the object is 4 meters per second, right? So accordingly it will be 4 into 4, 16 multiplied by 15. So it is around 120 joules, right? So kinetic energy will become 120 joules. Now, then potential energy. So therefore, once we see kinetic energy, which is half mv square, and also see, and once you see an example, so it is again coming in joule, right? Now, finally, what next is potential energy is actually the energy possessed by an object by virtue of its position or shape. Like if a rubber band is stretched and then released, it regains its original position. You can know, right? You understand? Now, when the rubber band is just stretched, energy is transferred into it. I mean, to it and stored as potential energy. So therefore, when there is a deformation in the shape of the object, then also we can say that potential energy is obtained. So if we find the key of a toy car and place it on the ground, it moves. When we win the key of the car, I mean to say energy is transferred to the spring inside and stored as potential energy. So if you lift an object to a height and releases it, okay, and it falls down. So when an object is lifted, energy is transferred to it and stored in the form of potential energy. That's what. So therefore, there must be a change in the shape or position of the object. Now, if you look at potential energy and its dependence, like of an object at a height, a particular height, because chiefly we deal with the object's potential energy only at a particular height, right? When an object is raised to a height, what is the energy it possesses by the body? Its energy increases because work is done on its against gravity. That we know, and the energy present in such an object is called gravitational potential energy. So there are two different types again when it comes to potential energy: gravitational potential energy and the other one that we have seen. Yes, okay, just now in the form of spring, in the form of stretched rubber hand, that is shape. So here it is only height. Now, if an object of mass m is raised to height, now then the force, okay, required to raise the object is equal to mass into s. We know m into g. Now against the gravity, and then again when the force is multiplied with height or displacement, we get the work done. So work done here is equal to m into g into h rather. So mgh. So abbreviated as capital E suffix small p, that is potential energy, is equal to mgh. We can now do some of the small numericals based on potential energy is equal to m into g into h, that is product of mass into acceleration due to gravity and height. Now we can also do a small problem based on that, that is find the energy possessed by an object of mass 10 kg as, yeah, it has a height of 6 meters above the ground, right? So 6 meters above the ground. So therefore g is equal to 9.8 meters per second, h is equal to 6 meters. Right, so then typically mass will be 10 kg. So therefore, When the mass is 10 kg, then m is equal to, and g is 9.8. So, and m into g into height. So height is 6 meters. So therefore that we can consider around 588 joules it is coming. Transformation of energy, if you look at, so how the energy gets transformed. Because energy conservation theorem is applicable each and everywhere. So energy can neither be created nor be destroyed. One form of energy will be converted into other form. The conversion of energy from one form to another form is called transformation of energy. Conversion of energy from one form to another form is called transformation of energy. Like here, potential energy can be converted into kinetic energy and vice versa. Right? When energy is converted from one form to another, the total energy always remains the same. This is to be understood clearly, that total energy remains the same. So though it is converted into another form, the total energy, for example, when P is converted to Ke, the sum of P and Ke remains constant at each and every stage. The law of conservation of energy states that energy can, energy can only be converted from one form to another. It can neither be created nor destroyed. So the total energy before and after the transformation, it remains constant or the same. Okay, so just we can take an example here and to demonstrate and the same, like when you take an object to be allowed to fall freely from a height. So it starts at the start, the potential energy is more that because of height, and gradually, because there is no velocity as such, initial velocity being zero, so there is no kinetic energy. But as the object falls down, the potential energy changes into kinetic energy, and the potential energy decreases and the kinetic energy gets increased. So when the object is about to reach the ground, the kinetic energy is the largest. I mean to say, by the time it hits the ground with the maximum velocity, it tries and hits the ground. But the sum of potential energy and kinetic energy always remains the same. So potential energy and kinetic energy is constant. Potential energy and kinetic energy is equal to constant, right? Okay. So always it is constant. Potential energy and kinetic energy is always constant. Sum of potential energy and kinetic energy. See, when I say, because the sum means it is mechanical energy. The sum of potential energy and kinetic energy is called mechanical energy, because it is only mechanical energy. As per the terms involved, we can say it is mechanical energy of the body. Now, lastly, we have to study one thing that is called rate of doing work. At what rate, typically at what rate or at what time rate, if the work is being done, if you try to understand, then that is called power. So what power is nothing but is the work done per unit time. So unit of power is always watt. Okay, so that means just now we have seen work done with a unit joule, and time is always in second. So generally 1 joule per 1 second is said to be 1 watt. Okay, in this SI system, whereas in the case of CGS, there is another unit, right? So therefore 1 watt is the power actually of an agent like which does a work at the rate of 1 joule per 1 second. So 1 joule per 1 second is deemed to be 1 watt. So accordingly, we have other units like kilowatt. Okay, so that is as 1000 watt, and we can see 1000 watts. Now, finally, commercial unit of power. If you look at the commercial unit of power or energy, okay, so we say it is energy basically it is power, or you can say it is energy per second, just like work done per time, right? So commercial unit of energy is said to be kilowatt hour, which is of high importance with regard to electrical meters. So usually in the electrical meters, the energy is calculated at this rate, like 1000 watt hours or 1 kilowatt hour per 1 kilowatt hour. That means the unit of energy, that is 1 kilowatt hour, is said to be when 1 kilowatt of power acts for 1 hour. Or okay, when 1 kilowatt of power, it does some work for 1 hour, then you say, okay, 1000 watts into 1 hour is said to be 1 kilowatt. 1 kilowatt. So therefore, 1 kilowatt hour is nothing but 1000 watts into 1 hour. Again, 1 hour consists of 3600 seconds, 13 to 16 to 60. So therefore, in terms of exact joules also we can convert. So finally, it is nothing but in terms of joules, it is going to be 3.6 into 10 power 6 rather. Yeah, it is joule. So this is electrical energy, very commonly used in our domestic electrical systems. and is considered to be 1 unit. 1 unit. So here 1 unit means 1 kilowatt hour. This is how it is considered, and as per it, it is billed. So therefore, it is important for us to understand what is the unit of energy, particularly in our domestic systems like electrical systems and electrical meters. So 1 kilowatt hour means 1 unit. So in terms of units, we calculate and bill it, right? So for example, if there is just now, as we have seen, these many kilowatt hours if they consume, like for example, 3 lakh, 36 lakhs joules. Okay, it is joule second rather, exactly, not joule, right? So it is, that is how we can consider it. This is the entire thing about work, energy and power. So I think students, you people, so you study and get good concept out of it, and I think you fare well in your exams. Thank you.